Hello, everyone, and thank you for attending my talk. My name is Bob Steagall, and I'm here today to talk about and share some ideas regarding APIs and API development based on my experience as a C++ programmer over the last quarter century or so. As always, I was a little bit surprised when this talk was accepted, as it's not about programming per se. Instead, it tries to circle around the business considerations of selecting, using, building, maintaining APIs. It's my hope that we can chip away a little bit at the opacity that surrounds APIs and learn a little bit more about what makes them useful in a business context, and maybe help us value them or understand how to value them, put a dollar value on them in a business context. So, although the vast majority of the work that I do is in C++, this talk is not C++ centric, although I have to admit there are a few C++ isms that have crept in here and there. Now, as programmers, we use APIs every day, and whether it's at the library level or a subsystem or the individual component level, and in my experience, I found that using many existing APIs is often unsatisfying for lots of reasons. There's poor documentation, confusing interfaces, muddy or poorly designed abstractions, broken or missing or incorrect functionality. And so this leads me to the question of how can we distinguish between a good API and a bad API? And more importantly, how can we make the argument to our management that good APIs, whether we get them off the shelf or we build them in-house, are a prudent investment for our company? So this talk seeks to discuss these questions and perhaps provide some answers, shed a little bit of light on the issue. So we'll look at some criteria for evaluating the quality of an API, and we'll talk about the ideas of technical debt and software capital, and define a relationship between them and API quality. We'll also look at a simple iterative process framework for building APIs, which can help avoid technical debt and increase software capital as you build APIs, as you build components. And finally, I'll present some recommendations for evaluating APIs and using the process that I'll describe in your day-to-day work, and hopefully also, to some extent, some small extent, convincing management of our collective wisdom when we ask them for resources to get us better APIs. So I'll warn you right now that there's a lot of opinion in this talk. And since I'm the one in front of the camera, I'm going to assume that my opinion is the correct opinion, at least for the next few minutes. So that being said, let's jump into a somewhat sobering or possibly depressing topic: software failures. In 2018, Tricentis, a company that builds and sells tools for automated software testing, published a report called the Software Fail Watch. And in it, they documented 606 significant software failures that occurred in calendar year 2017. And they did some statistics, they added up some numbers, and they found that approximately half the world's population was affected by these failures. There was almost $2 trillion in lost revenue to businesses because of the failures. That collectively, software failures resulted in 268 years of downtime for those companies, and that the number of reported failures was distressingly 10% higher in 2017 than 2016. Interestingly, they found that the retail and consumer technology industries had the most software failures of any of the industries they analyzed. And I think I can see why, although I'm not certain, and I don't want to speak out of school here, but these are both highly competitive industries. They have fast development cycles, they have low margins, and in these industries, software development is considered a cost center rather than a revenue center. In May of 2020, Undo Software and a project done at the Judge Business School of Cambridge looked at testing and the costs associated with testing and test failures. And they found that on average, reproducing and fixing a failure costs about 13 hours of developer time. And overall, throughout the course of a year, about 26% of developer time is spent on trying to reproduce and fix failures that have been reported. And when they added all of this up, they came up with a number of about 620 million developer hours per year cost to industry at about $61 billion and about $1.2 trillion of value lost for shareholders. Now, I'm not sure how that value number was arrived at. It's certainly a very impressive number, but it's sobering, and it points to, in my opinion, deficiencies in our industry when it comes to producing quality software in general, not just with respect to APIs. So let's look at some specific cases. In 1985 through 1987, the Therac-25, which was a radiation therapy machine produced by Atomic Energy of Canada, was involved in 6 very serious accidents, and that resulted in 3 deaths. Due to multiple design flaws, this machine could accidentally give patients radiation doses, X-ray doses, that were hundreds of times greater than normal. Now, there were lots of flaws in the overall design of the machine, including things like the lack of hardware interlocks. But from our perspective as software developers, there were a couple of interesting things here. The first is that there were lots of concurrent programming errors, that is, race conditions, multiple processes or threads trying to read and write to shared variables at the same time. Another that was specifically called out in the report was a flag variable that was set by incrementing the variable rather than assigning it to a specific meaningful value. And when multiple threads or processes incremented this flag, occasionally that flag would wrap around to 0. And when that flag was at 0, it disabled the safety checks in the machine. So in a sense, these were failures of an API. In June 1996, the Ariane 5 exploded 37 seconds after it launched. And the problem was a data conversion from a 64-bit floating point number, a double, to a 16-bit signed integer. Now, apparently, this double, which was converted to an integer, accumulated during flight. It accumulated a value having to do with something having to do with the flight. And 37 seconds into the flight, the amount of value that had been accumulated in the double exceeded the value that could be represented by a signed 16-bit integer. And so the signed 16-bit integer wrapped around, and it caused the spacecraft to shake and vibrate, and eventually it exploded. In 1999, in September, the Mars Climate Orbiter burned up on re-entry to Mars. And this was a rather silly mistake, but again, an API impedance mismatch. A module which produced output in non-SI units of pound-force seconds was fed into a module which expected information to be provided in SI units of Newton seconds. And so there was just simply a units conversion problem, and it caused the orbiter to enter the atmosphere at too steep of an angle and crash. In August 2012, Knight Capital lost $460 million in 45 minutes. What had happened was there was a flag left in the software, or a flag in the software which was used to run automated testing was left enabled. And that flag turned on code that ordinarily would not be exercised or executed in production code. And what it did is it moved prices higher and lower and executed trades as quickly as possible, triggering 4 million order executions in 45 minutes. And it disrupted the prices of 154 stocks on the New York Stock Exchange. And tragically, of course, we're all aware most recently of the Boeing 737 MAX jet crashes that occurred in October 2018 and March 2019, killing 346 people. Boeing relied on a system called the Maneuvering Characteristic Augmentation System, or MCAS. And in the April 2019 IEEE Spectrum, a gentleman named Gregory Travis, who was a pilot and an engineer, software engineer, described what happened in layman's terms. He described the systems that failed. There's a lot of information there, and it's a fascinating article. But for our purposes, he summarizes the failure in 3 points. The first point is that Boeing produced, in his opinion, a dynamically unstable airframe, the 737 MAX itself, by placing the engines, making the engines larger and placing them further in front of the wings. It made the aircraft unstable. That's not as of much interest to us as software engineers, but the next 2 items I think are. Boeing tried to mask this instability with the MCAS system, which executed software in an attempt to right the aircraft when it thought that the aircraft was going into a stall. And finally, the software, the third point that he makes is that the software relied on hardware systems known for a propensity to fail, the angle of attack indicators, and didn't include any sort of provisions to cross-check the readings from the angle of attack indicators against other sensors, or even the duplicate angle of attack sensor that was on the other side of the aircraft. So based on what I can surmise, these are all in some way API failures. One part of a program was using a different part of a program incorrectly. There is a kind of impedance mismatch here, and information was being exchanged incorrectly between disparate components. So every presentation should begin with at least one definition that's borrowed from the fountain of all human knowledge, Wikipedia. So here's one to start us off. What's an interface? Well, in computing, an interface is a shared boundary across which 2 or more separate components of a system exchange information. And we all know that this exchange can be amongst software, hardware, peripherals, humans, combinations of these things. Alternatively, and I like to think of interfaces in this way, it's a little more concise, an interface is a well-defined boundary for information exchange. So let's look at another definition, and that of API. Wikipedia, again, the fountain of all human knowledge, defines an API as a set of clearly defined methods of communication between software components. Well, these are great and concise definitions of interface and API, but in today's software engineering world, the terms API and interface are very, very highly overloaded. We often use these terms almost interchangeably when we talk about the public interface that's exported by a link library, or the public interface that's exported by a module, if we have a programming language that supports modules, which C++ does now, or subsystems. The public and protected interfaces that are provided by a class in C++. The set of function signatures that arise from an overload resolution set in C++. The interface formed by the set union of a set of ordinary functions. The signature of a single function or macro, as well as messaging protocols and data formats. I mean, coming from the medical imaging world, sometimes you hear people talk about DICOM, which is a standard for exchanging medical image information. Talking about DICOM as an API, even though in many senses it defines data formats at rest on disk and message formats as data is transferred across wire. And of course, someone in the chat has just pointed out that I should also talk about REST interfaces. And so on and so on and so on. So we use these highly overloaded terms. So for the purposes of this talk, when I say API, what I mean to say is, or refer to, is the non-private interface that's exported by a library or a framework, as expressed by the headers, the source code, the modules, the executables, the libraries, and the documentation. And here I'm saying non-private because in C++, part of the interface of the class is its public interface and also its protected interface, which can be used by classes that inherit from it. So in other words, what I think I'm getting at is the publicly available or the non-private set of services that are provided by some thing that's supposed to be executed. So I'll assume that an API is more or less equivalent to, and it's associated with, a library of some sort. Not necessarily a linked library. Certainly in C++, we can have header-only libraries. And so I may use the terms API and library interchangeably. And when I say interface, then like Humpty Dumpty, it will probably mean whatever I want it to mean in that context. So a useful way of thinking about APIs is that they represent contracts, a contract between a component and its users, a precise and complete specification of guaranteed behavior that's observable by the user, and a specification which excludes implementation detail. The API specifies expected behavior by both parties, the party on each side of that boundary of information exchange. The library follows the rules on the service side of the contract, and the developer follows the rules on the client side of the contract. As we all know, APIs can have multiple implementations. Consider the standard C++ library. We have implementations from Clang, GCC, Microsoft, and some other lesser-known implementations. And in my opinion, this is an outstanding example of an API in the way that it's specified by the standard. I know that basically no matter which of these compilers I use, when I call a particular function that's part of the algorithms library, or I use a particular class, I know that the time and space complexity of the services I'm using are going to be the same. They're guaranteed by what the standard says they're going to be, and they're going to be no worse than what the standard says they should be. There is no surprise when I switch from one implementation to another. You know, modulo corner cases and bugs. There are also APIs by many domain-specific libraries, and I just mentioned DICOM. This is an API which has an international standard, just like C++. And there are a number of implementations that provide for the DICOM image storage format and DICOM image transport from node to node across the network. So why do we want to use APIs? Why do we want good APIs? Well, a good API is important to our software development efforts because it leads to higher quality code. It hides implementation details, which means there are abstractions and there's mental clutter that we don't need to experience in order to make our product better. A good API will support faster implementation and changes to our implementation and optimization. A good API will promote modularity in the products that we're trying to build because it is itself modular. A good API, probably the greatest benefit, is that it reduces code duplication because it prevents us from having to reinvent the wheel and implement the services that are provided by that API. A good API promotes code reuse, not only in the API itself, but if we are able to use the API effectively, we can create our own modules, which themselves can then be reused. A good API promotes parallel development, and by this, I mean multiple members of the team can use the API at the same time to accomplish their tasks. There's not a bottleneck waiting on someone internally to build the API for them. Good APIs promote better products overall, not just because of the software development reasons that I mentioned, but also because of things like documentation and testing. Good APIs promote longevity in our products. They hopefully contribute to our products having longer shelf lives and producing more revenue. At the end of the day, a good API reduces engineering costs in terms of both time and money. And the importance of that can't be overstated. So why would we want to avoid using APIs or a particular API in general? Well, of course, we have the problem of domain mismatch. The API at hand or the one you're evaluating may not quite solve your problem, or if it does so in an awkward way. For example, if I'm doing some image processing and I need a library that does FFTs, Many libraries have very fast 1 and 2-dimensional FFTs, but if I'm doing 3-dimensional MRI volumetric imaging and I need to do 3-dimensional FFTs and my library doesn't provide that, then of course it's not a good fit for me. It doesn't meet my requirements. Or perhaps the library I'm using is optimized only for power of 2, but I need FFTs that have arbitrary size. One of my biggest pet peeves, documentation. Poor documentation or no documentation. It makes it very difficult to learn how to use an API or even understand if the library behind the API is working correctly. It's very much analogous to a verbal, ambiguous, fuzzy contract. Think of two drunks talking to each other in a bar. APIs could have closed or proprietary source code. In the C++ world, this would be headers and the binary linked libraries and the documentation. Now, closed source code can be great, at least until you find that there's a problem. You can't see the source code underlying the API to understand what might be wrong or to find a workaround, or even if your code is the problem or their code is the problem. You can't change the source code to fix the problem. Many times you can't provide an environment to the vendor that provides the APIs that allows them to duplicate the problem to see if they can fix it. Ultimately, closed and proprietary APIs could present problems to your project because they prevent quick reactions to problems. And also, in a sense, they put your schedule at risk due to actions of a third party that you can't control. Now, of course, I'm making it sound worse than it is. There are many, many third-party APIs, closed source, that you can buy that are great and do the job, but occasionally you come across something that doesn't work well, and then this can be a problem, especially if you're working in a niche area where you have no open source options and the closed source options are limited. You can also run into license restrictions. The API, the licensing terms that come with an API may not conform to your business requirements. There are monetary costs to assume when you're purchasing a commercial API, but there's also intellectual property costs to consider, when you have a mismatch. Say, for example, you want to use a library that's GPL'd, but you can't mix the GPL into your code because you're using an incompatible license, and it's a business requirement to use that license, which is incompatible with the GPL. Otherwise, there are all kinds of other cases where APIs don't fulfill the requirements for the product that we're trying to build. They could be incorrect, they could be inefficient, they could have a reputation for poor support, they might not support the platforms or compilers that we're interested in, et cetera, et cetera. There are all kinds of opportunities here for requirement mismatch. Something I'd like to emphasize that I've discovered a lot of people don't understand or appreciate, managers don't understand or appreciate, is that building an API is different than building an application. An API is designed for developers, and I was shocked to learn that developers are not like ordinary users. We tend to be a little less patient and a little pickier. Now, multiple products may and hopefully will share a given API. As I mentioned, the STL is about 28 years old now, depending on how you count it. And I can remember downloading it from HP Labs when it was publicly released in 1994. Of course, the problem then was finding a C++ implementation that could actually compile it. As a product, APIs have some unique maintenance and evolution challenges. Things like bug fixes, or for example, in C++, ABI issues present unique problems in changing APIs or evolving an API that you're responsible for. API developers have to worry a lot about backward compatibility, which is typically a very high priority for them. Breaking changes have to be very carefully considered and managed, and robust change control is absolutely critical to maintaining product quality, your sanity, and the sanity of everyone that works on the product that produces the API or uses it. I think that good documentation is extremely important, and you're going to hear me say this many times during this presentation. Users have to be able to learn how to use an API effectively. And this is not normally the case with application code. Extensive testing, and preferably automated testing, is also extremely important. I would say documentation and testing are two of the top three issues for me with APIs. Users have to be able to trust that an API is doing what it claims to be doing. And one important way of building that trust is through testing, hopefully transparent testing that users of the API themselves can repeat. Building APIs is typically more dangerous than building an application. APIs can be a force for good or for evil. A good API can help save time and money for every product that uses it. Conversely, a bad API will very likely cost time and money for every product that uses it. As a consequence, APIs have a multiplier effect. And it's important to keep that in mind as you sit down to design a new API or modify an existing API or evaluate a COTS API that you want to purchase or free and open source API that you want to use. So how do we talk about APIs in the context of a business, and how do we assign value to them? These are difficult questions. I don't think anyone really has a universal, easy to apply answer. I know that I don't have such an answer. And if I did, if I had a magic formula, I'd sell it to somebody and lay on the beach somewhere and earn 20%. So why are so many APIs so awful? Well, bad APIs are easy. They're easy to create. For every right way of doing something, there are lots of wrong ways, and just pure statistics, it's easy to pick a wrong way than the right way. Doing things the wrong way is inevitably a lot easier and a lot faster than spending time to do things the right way. It's usually less expensive in terms of dollars and time to make a Band-Aid incorrect solution and move on. Bad APIs often represent and are the result of taking the path of least resistance. On the other side of the coin, good APIs are difficult. They're incredibly difficult. Finding the right way to do something can be time-consuming and it can be costly. Many years ago, about 16 years ago, I was in a company where we built a functional MRI, an fMRI product. And I had a particular math problem to solve to implement a particular kind of imaging in the product. I didn't write any code for about 6 weeks. I had pencil and paper and marker and whiteboard to solve this math problem. Once I solved the problem, I was able to implement it in code, and that implementation gave us a very significant business advantage over our competitors at the time. And I consider myself at that position have been very, very lucky to have a manager who valued this kind of work and gave me the freedom to explore the math and solve the problem, and wasn't worried about me making noise by typing on my keyboard. So the right way is usually much more expensive. But as a result of that, we're subject to more unpredictable schedules, especially in greenfield development of APIs. And often API development is subject to managerial skepticism. One of the things I've heard before from upper level management is, why are you engineers always trying to recreate the wheel? Why can't you just be happy with what you already have? Fix it and move on. And I sort of think of this as being inept management. They don't understand the problem at hand, and they don't understand the losses the business will suffer if they don't pay attention to this problem. So let's talk about technical debt. Technical debt is a term that was first coined by Ward Cunningham in 1992, and he wrote, "Shipping first-time code is like going into debt. A little debt speeds development so long as it is paid back promptly with a rewrite. The danger occurs when the debt is not repaid. Every minute spent on not quite right code counts as interest on that debt. Entire engineering organizations can be brought to a standstill under the debt load of an unconsolidated implementation, object-oriented or otherwise." Lots of people define it as the cost of additional rework caused by taking the easy way out now instead of a better solution that would take longer and have a longer life. And it was originally intended to be a metaphor to capture the trade-off between short-term compromises in order to make progress and long-term progress that you ultimately do by refactoring. It's very much like monetary debt. Just like you would borrow money now to buy a house or buy a car, you pay it off over time. The idea is that I would make some short-term compromises, but I would be a good citizen and pay that debt over time. Ultimately, I would get to the spot where I wanted to be. And of course, in the real world, that doesn't happen very often. Technical debt tends to grow non-linearly, almost exponentially, and it accumulates interest. It gets to the point where it increases time to add new features, and that is what contributes to the cost and complexity that grows exponentially. Eventually, the cost of adding features is greater than the cost of a rewrite. You get to the point where the wheels are come off the wagon, you're pulling the wagon through the mud, and the cost of adding new features is greater than the cost of just starting from scratch. And ultimately, technical debt is in sort of this one-to-one relationship with a concept known as software entropy. So what are the kinds of technical debt? Well, briefly, we have code debt. And you can think of this as inconsistent, unreadable coding style, static code warnings, leaving messy code behind, which, yes, compiles, and yes, we think does the right thing, but is ugly and hard to maintain. We have design debt, which generally is evidenced by design smells and best practice violations. We have test debt, which is usually symptomatic, or the symptoms are that of not having test assets, having poor test coverage, having a haphazard, ad hoc, or even non-existent testing regime. We have documentation debt, where we have missing or poorly written, outdated, or incorrect documentation for the important aspects of the product. Here's a diagram provided to me by David Steagall at Bloomberg, which is intended to show, in a qualitative way, the growth of technical debt over time if no efforts are made to service or reduce that debt. I know I have, and I expect we've probably all worked on projects where we've felt like this was happening. Now, this is a qualitative diagram, and it's intended to describe a concept rather than provide hard numbers. A couple of years ago, I came across a very apt metaphor for technical debt in the context of software engineering that I thought was amusing and also so true to life that I couldn't leave it out of presentations like this. And I've heard it called the kitchen metaphor. So we're building something at the beginning of the lifetime of a product, be it an application or an API itself. So we start off with a clean slate, a clean kitchen, if you will. Everyone has good intentions to work together, clean pots and pans and dishes as we go, and so the work begins. But there are inevitably problems, and so you make a few compromises. Some pots don't get washed, some dishes don't get washed, the stovetop goes uncleaned for a little bit. And so you leave a few dishes in the sink. But you promise yourself, I'll wash them later and put them away. But you're a victim of your own success. The product or the project was very successful, and management says, we've got to get a new release out, the next release right away. We need to ride this gravy train for as much as we can. So you leave the debt untouched or unserviced, you leave the dishes in the sink, and you make some more compromises to get the next release done. You end up with more dirty dishes in the sink, more accumulated technical debt. Now the cycle repeats itself. Success builds on itself. The cycle repeats itself, as it always does. And after a few releases, your project begins to look like this. Metaphorically speaking, that is. I expect we've all probably worked on projects like this and experienced this firsthand. And I can say that I've worked on at least one project in my career where my greatest hope for that project was that the code would be as organized as the sink that you see in this picture. So what are the causes of technical debt? Well, there are a lot of causes, and I'm going to list some that I've experienced personally. Insufficient upfront definition. This is when companies, organizations, departments, teams try to build something and they don't know what they're building? How many times have we wondered, what the heck is it we're trying to do with this product or this module or this library or framework or class? Last minute specification changes. Someone in management or someone in a position of authority says, wait a minute, this has to change, even though you're 2 days away from delivery. Business pressures. There's a constant pressure to produce revenue and take shortcuts, reduce costs to the greatest extent possible. Changes in business needs. By this, I mean perhaps the business has changed a direction. And now the software that you used to write as a revenue center has for some reason become a cost center for the company. And this leads you into the mindset, or management into the mindset, of reducing the cost of software engineering. Lack of process. In this case, which I've seen many times, there's a cowboy coding culture and nobody knows what they're supposed to be doing or when things are supposed to be done. There's a lack of understanding of the process, a lack of understanding of what we're trying to build, a lack of understanding of the problem domain, or just a lack of understanding in general. Tightly coupled components and or monolithic architectures. Teasing these things apart in order to modify them or use them or fix them can be a very difficult and time-consuming proposition. Little or no testing. How many times have we walked in as new employees to a shop and found out there is no test plans, there is no testing program, there's no test regime, there are not even any test programs. We execute tests by running the programs, and if they fail, then we log bugs. Little or no documentation. Again, one of my greatest pet peeves. How can anyone, user or team member, know how to use the product or how to develop the product if they don't know what it's supposed to do and it's not documented somewhere in a place that every stakeholder can agree on? Little or no collaboration. Occasionally, you'll see teams, or you'll be a member of teams where the team members don't actually communicate with each other. Everyone does their own thing, and they hope at the end they can integrate it all together. Or the team lead will take heroic measures to integrate all the changes made by these team members who don't really interact. Little or no version control. Fortunately, none of the teams that I've been on, this has been a problem, but of course, you can read many horror stories about products being released with no version control and the business losses that have happened because of that. Delayed refactoring. By this, I mean not servicing technical debt when you can. And just the delay of the refactoring itself can lead to growth in technical debt. It seems to be this truism that, technical debt will grow over time if you don't do anything to service it at all, even if you're not really making any changes that themselves contribute to technical debt. Just by adding something in another part of the application that may add to the overall complexity of the thing, even though it doesn't affect those problems, that the sources of technical debt, in and of itself increases complexity and increases technical debt. You have a lack of alignment to standards. If you're working in a regulated industry like the medical imaging industry or avionics or aeronautics or the nuclear power industry or the automobile industry where consumer safety, actual physical safety, is an issue, lack of alignment to standards is a source of technical debt. Lack of ownership. When team members refuse to take ownership for their mistakes, or management holds team members responsible for their mistakes but doesn't give them ownership over the decisions that they make. Poor technical leadership. Of course, this is when your management doesn't understand the underlying technology that you're trying to build and asks you or orders you to build things that don't make any sense. And finally, poor business leadership. This is when management can't decide what product it is that they want to build. And unfortunately, I've experienced this a couple times, and the companies that had this problem subsequently went out of business. So let's talk about software entropy. The first definition is from Ivar Jakobsen in his book published in 1992 called Object-Oriented Software Engineering, a Use Case-Driven Approach. And he draws an analogy here to the second law of thermodynamics. The second law of thermodynamics in principle states that a closed system's disorder cannot be reduced. It can only remain unchanged or increase. A measure of this disorder is entropy. Jakobsen says that this law seems plausible for software systems, and as that system is modified, its disorder or its entropy tends to increase. Thus, he calls it software entropy. Another definition from Webopedia, and I really like the first sentence of this: software entropy is the tendency for software over time to become difficult and costly to maintain. Martin Fowler doesn't call it software entropy, he calls it cruft. So in theory, it may be better to redesign the software in order to support changes rather than building on the existing program. But keep in mind, redesigning software is more work and more cost, and you run the risk that redesigning existing software has the potential to introduce new bugs and problems. Redesigning and rebuilding things or extensive refactoring is not always a cure-all for cases of severe technical debt. Everything has to be considered and balanced. So what are some symptoms of software entropy? How do we know when it's occurring? Well, feature creep is a big symptom. Product development or management wants features to be added to a product that extend beyond the basic functionality of that product. And they don't really add any value to the user, but they do become marketing points. You also have gold plating, which is when developers add features to products that are frivolous and don't add real value to the product. And in a sense, the way I think of these or distinguish these two things is that feature creep is unnecessary features added to a product that have been approved by product management. Management is losing sight of what the customer needs. Gold plating is unnecessary features inserted by developers without approval. And I find that, sometimes this is because developers are bored, or they're experimenting with new technology, or they just think their idea is such a great thing that it should be part of the product and users are going to love it. I think very rarely is that actually the case. We also have brittleness, which is when older software appears to be reliable, but it fails and fails badly when it's presented with unusual data, unexpected data, or it's altered in a way that seems minor or harmless. And usually this is a kind of thing that's caused by algorithms that don't work well for the full range of input values, or maybe the range of input values has expanded, data structures that restrict these values, dependencies that are too rigid, and sometimes a lack of institutional knowledge transfer from the older generation, perhaps, that built this older product to the new generation, which has to maintain and service it. Another thing which we've all come across, I'm sure, is bloat, where successive versions of a computer program become perceptibly slower. They use more memory, more disk space, more processing power. Their requirements to use them grow over time for no good reason. And a corresponding symptom is software rot, which is a little different than bit rot. And software rot is sort of the slow deterioration of performance over time, even though actually nothing has changed. And nothing has changed in the software itself. And in this case, it's more something that's due to changes in the environment in which the software runs. And the software is no longer running optimally in that environment. And thus, its performance appears to slow down. But in both of these cases, we experience these things in common products all the time. There are products, the first version of which I bought in the mid-90s to do particular business tasks. And they took X number of seconds to open up and present the user interface to me on my Windows NT screen. And here I am 25 years later with computer systems, which are arguably 2 or possibly 3 orders of magnitude faster than the hardware I was running on in 1995. And yet the amount of time it takes to open those applications is exactly the same. I don't understand that. So let's talk about the inverse or the converse of technical debt, software capital. What is it? Well, software capital can be defined as the cumulative technology that can be redeployed to new situations. And this is a term that was coined by a gentleman named Dean Zaris in 1996. It's intended to reflect software as an asset rather than a liability. There's the basic accounting formula, assets equals liability plus equity. And I think what Mr. Zaris was trying to do was to account for software on the asset side of the ledger, and because we had technical debt on the liability side of the ledger. There was a great article, and I think it was in IEEE Software about 10 years ago, from an author who proposed that the generally accepted accounting principles in the United States should be modified so that CFOs and accountants were required to put actual dollar numbers on software technical debt, and that it should appear on the company's general ledgers as actual liabilities. Well, that's never going to happen, and I think if it did happen, a lot of CFOs would have heart attacks. So done correctly, software capital becomes a tool set for application developers to more rapidly respond to business needs. It's intended, the idea, of course, using good infrastructures, good APIs, is they raise the starting point from which a solution begins. Lots of wheels don't need to be reinvented. We reduce our time to market with software capital, and good software capital pays dividends rather than costing interest. In a way, in a very serious way, it is the exact opposite of technical debt. And building software capital is really, in my mind, the holy grail of API developers, because it goes directly to the idea of reuse, which leads to saving time and money, which in the long run leads to happy management and hopefully job security. So how does it work? What was Zaris's idea? Well, on the right side of the slide here is a table that was part of an article published in Hacker Noon in 2016, which describes application developers and software capital developers in the two different columns and different attributes that apply to those two classes of, if you will, categories of developers. He imagines two separate development teams, application developers and software capital developers. And I read software capital developers as being infrastructure or library or API developers. The application developers service the business unit needs directly. They implement the domain logic, the business logic that the business needs to sell its services or its products. Software capital developers provide the foundation or foundations that are used by the application developers. And the idea here, of course, as I said, is to enhance product quality, to enhance developer productivity on the application developer side, and to promote reuse across the enterprise. In this model, both sides leverage their strengths. Application developers are typically those that have a better or more deeper understanding of business rules, and they have the domain knowledge of the domain in which the business participates. And software capital developers tend to be a little more focused on lower level issues, software infrastructure, software interfaces. They're typically more interested in design and development in and of itself and the interconnection of software and software to hardware than, say, application developers are. And I'm overgeneralizing a little bit, but I think this is reasonable characterizations. So here's a diagram from Mr. Zaris' article. You have business unit users, business unit and end users, and they communicate their needs to the application developers. The application developers look to the software capital developers to jumpstart development because the software capital developers provide infrastructure that they can build upon. The software capital developers send their results and interact with the application developers, and the application developers receive those results, those tools. They provide feedback to the capital developers, and you have this feedback loop until you get to the point to where the software capital developers are are satisfied that they delivered good foundational components, and the application developers are satisfied that they've used those good foundational components to build good applications. And then they provide those to the business unit end users. In reality, sometimes this works and sometimes it doesn't. I worked at a company that had a model very much like this, where I worked on an infrastructure team, and there was a sibling team that had a product that used our infrastructure. And that product worked very well and just made a ton of money for the company. On the other hand, I was involved as a supplier for a Fortune 500 company that had implemented this model internally, where they had an entire division whose purpose was to provide software capital for application divisions. And there was a lack of communication and hard feelings, and eventually got to the point to where none of the application teams would use any of the foundation built by the software capital team. Eventually, as I understand it, that software capital team was disbanded. Now, this sort of takes a 1990s old-fashioned or traditional view of software engineering. It's a little more stovepiped than what we see today in our full-stack teams that most of us are members of. But even so, in full-stack teams, it's been my experience, at least, that there always seems to be a division of labor amongst the team members, whether it's deliberate or unconscious. And team members tend to categorize themselves or place themselves in one of these two roles of software capital development or application development. So here's another diagram graciously provided, again by David Steagall, that is intended to qualitatively convey that there comes a point in time in which the software capital-based approach will cost less than the technical debt approach. And importantly, past that point in time, the difference between the two approaches, the savings, grows exponentially. So in summary, technical debt versus software capital. Technical debt, it's bad. It's easy to create. Software capital is good. It's difficult to create. Technical debt is inexpensive to create. Software capital can be quite expensive to create. Technical debt usually refers to and results in components and software and architectures that developers and programmers are forced to reuse, under the gun, so to speak. Whereas with good software capital, good tools, good infrastructure, people will voluntarily reuse things, and they'll want to reuse things because they realize that this underlying software capital is helping make my work product better. Technical debt usually results from having a narrow focus, trying to fix an immediate problem and moving on to fix another problem. Whereas software capital is usually developed having a wide focus, thinking about the needs of the user and trying to anticipate what happens in the future. Technical debt usually results in architectures and codes and designs that are ugly. Whereas if you're lucky and you've done your job, well-designed software capital is at a minimum elegant, maybe beautiful. Technical debt usually results in solutions that are incomplete, whereas software capital results in solutions that can be considered complete. Technical debt increases our time to market, whereas software capital reduces our time to market. Technical debt increases our costs in the long term, and software capital reduces our costs in the long term. So I've told you all of this because I'm trying to lay out a framework for deciding whether or not an API is good or bad. How do I value an API? Well, let's talk about that. There's a great quote in the chapter 1 of Clean Code from Bjarne Stroustrup, Clean Code being the book by Robert C. Martin. And this is an excellent quote. "I like my code to be elegant and efficient. The logic should be straightforward to make it hard for bugs to hide. The dependencies minimal to ease maintenance. Error handling complete according to an articulated strategy, and performance close to optimal so as to not tempt people to make the code messy with unprincipled optimizations. Clean code does one thing well." Well, think about the adjective in those first two sentences and substitute the word APIs or libraries for code. And this quote really nails down what it is we as API designers and developers are trying to accomplish. So how do we characterize the quality of an API? What are the goals? How can we describe the quality of an API? Well, in my mind, the first such is readability, the ability to look at code, design documents, documentation, and read it. Is it actually readable? Secondly, is it understandability? I actually see readability and understandability as being two distinct, different things. And readability is a necessary precondition for understandability. In a sense, in my mind at least, readability is a little bit like syntax. Understandability is a necessary condition for minimizing cost. And in a sense, it is like semantics. And it's not a very good analogy, but it works for me. But ultimately, I very firmly and very strongly believe that when it comes to designing APIs and managing code, understandability is everything. It is just everything. And to that end, I'm going to provide a couple of quotes here from Grady Booch and Dave Thomas to help me prove my point. Grady says, clean code is simple and direct. It reads like well-written prose. One of the best sentences ever in software engineering. Dave Thomas says, clean code can be read and enhanced by a developer other than its original author. Now think again about the adjectives in these quotes. And again, substitute the word API or libraries for code or clean code. And these describe our goals. I think Dave Thomas's quote is very interesting because it emphasizes not only readability, but the ability for other people who didn't actually author the code to modify it or enhance it later. He also mentions that testing is necessary for code quality. And he mentions minimal twice, emphasizing the principle that smaller is better. He also mentions literate, and I think this is a shout out to Donald Knuth's idea of literate programming. But the bottom line, at the end of the day, code should be composed and represented in such a way that it's readable and understandable by humans. So if we go back to our quality goals, the next one I'd like to talk about is conceptual integrity. In The Mythical Man Month by Fred Brooks, he says that conceptual integrity is the most important consideration in system design. And it's really the quality of a system where all the concepts and their relationships with each other are applied in a consistent way throughout that system. Another term that I coined, and is important in my brain at least, is that of mnemonic consistency. And what I mean by it is that interface patterns and idioms that appear in the interface are reused as much as possible and as consistently as possible throughout an API. And this is to promote learning and reduce memorization. In other words, if I learn how the interface looks and feels in one place, I should be able to go to another place in the API and feel more or less at home and understand what I need to do. We have correctness, which to me means that an API does exactly what it says it will. We have testability, which means to me, not only is the API itself testable, but the API is usable in such a way that it promotes testing of your products. Of course, we have performance, which everybody wants, and in which we specify our requirements for runtime performance, memory performance, disk space performance, all different aspects of performance. Finally, a good high-quality API increases software capital. And if you think about it, if you fail to achieve any of the first 5 or 6 items in this list, in one way or another, you're actually contributing to technical debt. So how do we know if an API is good or bad? Are good and bad even reasonable or relevant adjectives for us to use? I considered effective and ineffective, desirable, undesirable, elegant or inelegant. But ultimately, for convenience and perhaps lack of imagination, I ended up with the terms good and bad. So I'll define them right here. A good API is an API that mostly increases software capital, and a bad API is one that mostly increases technical debt. So I'm going to provide some characterizations, and I think they're intuitive, but they're not orthogonal. They're not quantitative, they're not exact, they are squishy, they are nebulous, they are subjective. To use a linear algebra analogy, what I'd like to give you is a nice clean set of orthogonal basis vectors, but That's pretty much impossible. And so what you're going to get is something that looks like this. So what are some characteristics of a bad API? It's incomplete. It doesn't do its job. It fails to meet its requirements or specifications. It's unstable. It's untested. It's undocumented. It has an inconsistent design, an inconsistent structure, or inconsistent or bad naming policies. It is unnecessarily complex, leading to too much memorization required to use it. It's unnecessarily difficult to learn, perhaps because of its unnecessary complexity or its lack of documentation. It's written from the perspective of the implementer, in that it inconveniences the user to the benefit of the implementer, and it requires repetitive boilerplate code to be used. If you'd like the canonical example in my mind of this, just look at the select system call, which is part of Linux or Unix. It's indecisive. A bad API passes the buck to the user. And a good example of this is using enumerations to specify behavior in a portion of the interface rather than using types. A bad API will unnecessarily expose its implementation, with the problem that users will ultimately, sooner or later, come to rely on that exposed implementation in their code. So along those same lines, there are design smells that go with an API. A bad API could have missing abstractions, and in the abstractions that it presents, encoded strings are used to represent a desired abstraction rather than representing abstractions in code. We use commands or we use enumerations to specify behavior rather than types. Multifaceted abstractions are when an abstraction tries to do too much, like the kitchen sink. We have it do everything, big fat interfaces. Deficient encapsulation, when access to parts of an abstraction is public, and it shouldn't be. And again, it will lead to unnecessarily coupling with client code as client code comes to depend on those portions which are public but which should be private. Unexploited encapsulation is when we use type checks at runtime to vary behavior rather than using language facilities. So in C++, for example, this would be using type checking through enumerations or dynamic cast rather than using inheritance when it's called for. More design smells, duplicate names. How often have you run across things like multiple things in a class hierarchy or in a framework called timer or date, which have very similar names, and you're not sure from the name how it's to be used? One example of this, in my mind at least, is in the standard C++ libraries exception hierarchy. I find the exceptions are confusingly named, and every time I want to use a standard exception, I have to go to cppreference.com or look up in a book, what is the name of the thing that I'm actually trying to throw as an exception? I can never remember which is which. Duplicate implementations. You see this a lot on large projects where the wheel is reinvented multiple times. And this can happen because you have types that are marked for non-extensibility, or you have team members or organizations that are contributing to a product that don't communicate with each other, and it just ends up that the wheel gets reinvented. You have broken modularization, and you see this when there are bits of functionality that are spread out amongst multiple services, multiple classes, and multiple objects, when it really makes sense for them all to be part of one class. You have the idea of insufficient modularization, where you have something that's fat, and it could be further decomposed into more succinct, more concise modules. Now, of course, we always have occasionally run into cyclic dependencies when two things depend on each other directly or indirectly. We have unfactored hierarchies where you may see duplication in the functionality or behavior of siblings in a class hierarchy or cousins. You have broken hierarchies where a base type and its derived type do not correctly implement an is substitutable for relationship, meaning that inheritance will be broken and the inheritance and invariance that govern the derived type won't be observed. And we have cyclic hierarchies in inheritance where in some way a derived type depends on its base type and vice versa. So how do we characterize good APIs? Well, a good API solves a problem correctly. It provides satisfactory performance. It's composed of manageable, understandable pieces. Good APIs are built with common, well-understood idioms, patterns, and best practices. Good APIs are decisive. They don't pass the buck to the user. They implement the behavior that they say they're going to implement, and they make as many reasonable decisions as they can on behalf of the user. A good API is designed from the perspective of the user. The words and constructs that it uses are chosen to be reflective of the way a user would think. It behaves consistently and follows the principle of least surprise. You can use it and know that you're not going to get surprising results or surprising behavior. It states and observes the contracts to which it will adhere, meaning that there are no surprises in terms of no surprises in behavior. A good general purpose API, like the STL, will be policy free. It will leave as many choices as possible open to the user because that's its mission. Whereas special purpose APIs, like the DICOM libraries that I've mentioned before, might be very policy rich. They make a lot of decisions on behalf of the user because they need to in order to implement the strictures of the DICOM standard. A good API is stable and it's documented and it's tested. And it will behave consistently at compile time and runtime. The documentation will be complete, especially with regard to error handling, so you'll know how to handle errors when they occur. There's reasonable code coverage in its test suite, and at a minimum, you have test result transparency, if not test suite transparency. A good API will be minimally complete. It won't overpromise. Every public element is part of a contract. It makes a promise to forever support some facilities. Once you release an API, removing that is actually difficult. It uses both kinds of polymorphism wisely. It uses compile time programming when it makes sense, and it uses runtime inheritance, runtime polymorphism when it makes sense. It doesn't impose inconvenience on the user, and it has just the right amount of convenience interfaces. Good interfaces, in my mind, are not as lean as skeletons. There's a little bit of fat there. There's a little bit of extra flesh, which can make life easy. So you don't have to write the same wrapper functions all the time that group important combinations of arguments to aspects of an interface. A good API is ergonomic in that it's easy to read and understand. It's discoverable through mnemonic consistency. As I mentioned before, if you can understand part of the API in one place, you can understand it basically in any place. It's easy to use correctly, and it's difficult to use incorrectly. It's consistent in structure, naming, and usage. Again, mnemonic consistency. It's mostly orthogonal. Convenience interfaces that I mentioned before reduce orthogonality, but they do promote productivity. It helps the caller, it helps the user be effective. It provides the extensibility reasonably. It provides reasonable extensibility that the user may need in the future. It provides robust resource of its management, robust management of its resources, so you don't have to worry about resource leaks. In some sense, it's platform independent. So if you need to move your application from platform to platform, it manages that well. A good API will be loosely coupled, meaning that it's modular and it's layered. Coupling in the API will be by name only. Any redundancy that appears in the API would be intentional and minimal, and also documented. It hides implementation details judiciously. Sometimes you need to expose implementation details, especially if you want to make performance guarantees. It uses physical hiding and declaration instead of definition, especially in C or C++. It uses logical hiding through encapsulation in the class interface. It hides implementation to the greatest extent possible through the use of member data and member function, and even nested classes or types that are necessary for a given type to carry out its mission. So how do we build a good API? Is there a process or process framework that we can follow? Well, there's no perfect answer. And like I said, if I had it, I'd sell it and I'd be laying on a beach somewhere earning 20%. So if I can pontificate for a moment, when I've run teams in the past, I've tried to impart upon them what I call the 4 C's. Clarity of purpose, understanding your goals and why you're trying to achieve those goals. Clarity of thought, understanding the problem. And then once you actually understand the problem, understanding the solution that you propose to implement that solves that problem. Clarity of expression. And by this, I mean the ability to clearly describe the problem and your solution to others. In other words, can you convince others that you understand the problem and that you've solved the problem? And finally, the 4th C, neatness counts. And by this, I mean the presentation of your solution is just as important as the solution itself. A well-presented solution promotes understandability, which, as I said before, is everything. And when you're designing APIs, when I think about users, I see 3 categories, each with different expectations. You have casual users who want maximum ease of use, a minimum learning curve, a good experience and productivity right out of the box. You have power users who want ease of use combined with some ability to customize behavior and performance, especially because they're trying to do something that improves performance of their product. And you have expert users who want maximum customizability because they want to solve very highly specialized problems. And they're in search of the very highest performance. So as you work on an API, if you're lucky enough to be building one, keep in mind which category of user you're writing for. Where does it fall on this scale? I mean, clearly it's a spectrum of user capabilities and expectations, but I find this is a nice, easy to remember way of thinking about the level at which an API should be created. On process, a good process increases productivity. Use metrics to the extent reasonable to track product. A good process helps you control complexity of the process itself, of people and the work product. A good process helps you select the right tools and technology. And perhaps most importantly, a good process defines how, when, and by whom the various development activities comprising a product should be carried out. Because of these things, assuming these things all occur, a good process can help improve software quality. A good process will use recognized best practices to help carry out these objectives. It will promote software asset and tool standardization so that you can reuse assets you've created before, and you can also reuse tools that you know work correctly. It enforces consistent and transparent change management. So let's look quickly at a couple of different ideas for processes. We've all seen the old classic waterfall process where requirements are done, they feed into design, which feeds into implementation, which feeds into verification and validation, which feeds into maintenance. Well, the classic waterfall process is logical and simple, and it was the first such engineering process. It's appropriate and can work well for small or trivial projects or projects where the focus is very narrow and it's difficult to get out of your lane, and the domain is very well defined, and perhaps the amount of change that needs to be implemented is not very great. However, it suffers from the obvious fatal flaw for any non-trivial product. It delays the recognition and mitigation of risks until near the end of the process. As the process moves forward, it becomes more and more costly to fix defects that occurred at earlier places in the product. a project. So there's the old saw, if an implementation defect takes $1 cost to repair, then a design defect will cost $10 to repair, and a requirements defect will cost $100 to repair. I actually think that those ratios are underestimated. So how can we improve the waterfall model? Well, it's a little bit like the old joke, how do you eat an elephant? One bite at a time. You work in a way that is iterative and incremental. In each iteration, you add a subset of new capabilities. You review and adjust your requirements multiple times to make sure that you're building the right thing. You review and adjust your design multiple times to make sure you can implement what your requirements say you should build. You address your highest risk elements first. You build, you test, and integrate and document continuously over the development lifecycle. You look for opportunities to reuse components. So in the act of creating software, there are a number of creative acts. And I've alluded to some of them in the previous slide. You gather and analyze requirements. You define and refine some subset of the API. You implement and refine the code that provides the functionality of that subset. You write or refine tests for that subset. And usually early on, these are unit tests, and you write higher level tests, system and integration and acceptance tests later. You always run all the tests and make sure that all the tests pass before you move on. You create and refine documentation for that subset. You build as you go. Overall, you're trying to answer the question, what am I trying to build? What services will it provide to its clients, and how will it provide those services? What's required of my API's clients? So if I had to draw a picture, a very simple picture, it would look like this. It's cyclical. We explore and understand the problem. We analyze, design, implement, test, document, evaluate. And we do this a few times. And when we're done, we're satisfied that we're done, we deliver. So as an exercise in writing code, if I were going to build an API, my member function that accomplished this might look like this. I would explore and understand the problem. And while the version is incomplete, I would do some iteration planning. I would analyze requirements. I would refine the design, write code, write and run tests, write docs, review and evaluate my work. And I would iterate in that loop several times until the version is complete. When I'm done, I would deliver the version. Well, in thinking about creative acts this way, things don't really happen this way in the real world. In real projects, these activities are almost always concurrent, and it's a little bit messier than what I've laid out there. So if I had to refactor my construction, my build function here, I would begin by incurring costs. Every project begins by incurring costs. And I would explore and understand the problem. Now, while my costs are still acceptable and my version is incomplete, I would do some planning, and then everyone would go off and do their own thing for a while. At the end of the iteration, I would wait for all of these activities to synchronize with each other. I would review and evaluate. And I would do this many times until either the costs are unacceptable or the version is complete, at which time I would like to deliver a solution. So if my costs are still acceptable and it's okay to ship, I would deliver. Otherwise, I would update my resume and move on. So if you know anything about process engineering, this probably sounds familiar to you, or if you've studied software engineering process. And this is very strongly derived from and akin to a process called the unified process. Originally, it grew out of Barry Beam's spiral model and was championed by Walker Royce and later Ivor Jacobson. But it looks like this. You have engineering disciplines along the rows, and you have time in the horizontal dimension here. So you have modeling, requirements analysis, design, implementation, testing, deployment. change management, project management, infrastructure and environment management. And what this diagram is intended to convey is that as the project proceeds over time, the emphasis on these different activities changes. And you need to plan your project to account for the different emphasis that you would have over time. And I have to say that I think that's really brilliant work. And in the projects that I've worked on before where I was lucky enough to use that process, I thought they worked pretty well. So we want to understand the problem. We want to be able to define the scope of the API. We need to define the completion criteria for the version of the API we're building. We need to specify specifically what does done mean, and we need to specify quality metrics and targets. We need to define the tools and conventions that we're going to use and the development environment in which we're going to construct software. And we need to agree on coding standards and guidelines. When we gather requirements, in doing requirements analysis, you may have heard of the acronym called FERS. The F stands for functional requirements, where you define features, capabilities, reusability, security, the capabilities and aspects of a product. The U stands for usability requirements. What are the aesthetics, the learnability, the understandability, the consistency, the documentation of a product? What are the reliability requirements in terms of availability or uptime, predictability, accuracy, acceptable failure rates? What are the performance requirements? How fast does it need to run? How much memory can it use? How efficient is it by some measure of efficiency? What's its resource usage, throughput, capacity, scalability? And supportability. How testable is it? How easy is it to install? How easy is it to maintain? This is sort of a classic requirements analysis process that's been around for 2 or 3 decades now. When you gather requirements, there are some questions to ask your stakeholders. What's the problem domain terminology? What are the important conventions in the problem domain? What mental models do they have that describe the problem domain? What tasks do they want to perform using the API? What's an optimal workflow to perform those tasks? And some questions to ask about the product itself. What are the valid inputs? What are the expected outputs? What data formats and protocols have to be supported? What compilers are expected to be used, especially for C++, where we have ABI issues to consider? Are there any restrictions on language features that can be used? Again, an issue with C++. What are the development environments in which the API itself may be used? Is it okay will it run on Linux? Does it need to support Linux and Windows? If it runs on Linux, does it need to support both GCC and Clang? Questions like that. What is the expected end user requirement? Where is it going to run? What are the resources that are going to be available to it? So another way of gathering requirements is through the use of use cases. And use cases are a technique for defining API behavior based on its interaction with external entities. And these entities can be other software components or end users. Use cases capture who does what and in what sequence. And they describe requirements from another perspective, the perspective of the user or the client of the API. So traditional requirements describe a system's capabilities, whereas use cases describe how a system interacts. And to use a perhaps weak UML analogy, traditional requirements are static. They're like class diagrams. They show one aspect of the relationship of an API with its clients. Use cases are intended to be dynamic, and they are somewhat analogous to like state charts or sequence diagrams in that they're intended to convey dynamic behavior. So we want to write good requirements. We want to use domain terminology. We want to describe requirements in the user's language. And requirements should be unambiguous. They should be consistent with other requirements, i.e. self-consistent. They should be complete. Good requirements don't specify the design. Requirements and use cases that are well written can be used to design and develop test assets. So you can expect to revise requirements several times, and don't expect to have perfect requirements coverage because it just doesn't happen. So, excuse me, okay. So it's important to review requirements. It's important to reassess the requirements at the beginning of each iteration. You need to understand if stakeholders have changed their requirements, if external constraints have changed. Requirements change all the time, and you need to account for the fact that they're going to change over the lifetime of your API development. And review ensures that the understanding of work that needs to be done is in synchronization with the stakeholders' expectation, the external constraints, and the stated requirements. So try to assess coverage and content, overall quality, individual quality. So I had to augment the picture a little bit. This is where API requirements review fits into the process. We're running a little bit low on time, so I'm going to skip ahead a few slides here. So if you'll indulge me for a moment. So I'll talk briefly about design and design review. There are a few slides in here which describe this, which I skipped over. It's important once you've created design to review that design. And it's important to understand at the end of each iteration, is the design meeting the requirements that we set out at the beginning of the iteration? So the design review ensures that the understanding of the work that remains to be done is in sync with the stakeholders' expectations, the constraints, and the requirements that we agreed on at the beginning of the iteration. So in a review, what we try to understand is, in a design review that is, have we adhered to all of the design considerations that have been specified for us in the requirements? Do we have requirements traceability? In other words, can we look at any aspect of the design and trace that design aspect back to one or more requirements? And if a design component can't be traced back to a requirement, then you have to ask yourself, do I really need it? Should it be part of the design? Is the design internally consistent? If you step back and look at it, does it make sense? Does the design meet the performance goals? Does the design meet the maintainability goals, whatever they may be for your product? And often forgotten, but also very important, is does the design meet any regulatory or compliance goals that may be set out for you in your industry? And finally, is the design understandable? And again, for the fourth or fifth time, I will say, understandability is the most important thing. It's everything when it comes to effectively building software capital. So here's a quick diagram that shows where design review fits in the process. So I'm going to skip ahead again because we are getting close to the end. And I'm going to talk about some of my recommendations. So my first recommendation when you're building an API, or in fact, any software component, but I think it's very important for API, is to integrate continuously. Make sure that you're constantly merging changes from your master branch or development branch or whatever you call your main line into your development workspaces before you do pull requests and merge your changes back up into your mainline development. It's important that your developers are frequently updated and see all of the most recent changes as quickly as possible, or at least as quickly as makes sense for your project. Always try to leave things better than you found them. Before merging, make sure that all of your unit tests pass and that the overall pass rate is equal to or hopefully better than that of the test suite when it's run out of your mainline or master branch. Always design with change in mind. Try to anticipate which requirements are most likely to change in the foreseeable or intermediate future, or whatever the appropriate time horizon is. And try to anticipate and build in reasonable facilities to accommodate those changes. Of course, you don't know exactly what the future may hold, but you can try to anticipate over some intermediate time horizon, what those might be, and build in hooks or facilities or extensibility or flexibility to account for those anticipated changes that might come in 6 months or a year from now. Remember the 4 C's. And if you can't explain what you're doing, if you don't understand what you're doing, you can't justify what you're doing in a clear or concise way consistent with the rest of the API, then just don't do it. And as you write APIs, you're going to receive criticism from people, and some of it may be unpleasant. I know I've received criticism in the past for things that I've done, which is not what I would exactly call polite. And so don't take it personally. People are busy, they are what they are. Your job is to try and absorb the nuggets of gold from the criticism that you receive and use those nuggets of gold to make the API better. Very importantly, used scenario-based design. And this is a technique I like quite a bit. Early in the product lifecycle, as you're working on an API, after you think you understand the problem and you have a solution for it, don't actually write and compile code. Use a whiteboard or pencil and paper to write pseudocode, and use that pseudocode as a way of helping you quickly formulate what the code itself will look like, what the design of the code is, and understand the user's point of view. I do this all the time. I'll write programs and APIs purely on pencil and paper or on the whiteboard before I even type in a single line of code and try to compile it. And that helps me find all of the dumb ideas I've had before I actually spend time committing them to disk. And then when you write real code, write it in the way that your API users would have to write. And this is sort of corresponds to use your own API. You know, the quickest way to uncover the shortcomings in your API is to use it yourself. And if it irritates you, imagine how irritating it's going to be to your users. And finally, in terms of the process itself, evaluate your work continuously. Viewed from a high level, is my API meeting the stated goals? Am I observing the 4 C's? Am I increasing technical debt? If I'm increasing technical debt, then how do I eliminate or reduce that debt? Conversely, am I increasing software capital? If I am increasing software capital, then what more can I do to get more software capital or reduce existing debt to increase the capital to debt ratio? In other words, what improvements can I make to add to software capital, reduce technical debt, and make my API and the products that use it better products overall? Okay, well, I think we're out of time, a couple minutes over. Thank you, everybody, for coming. I appreciate it. And I just want everyone to know the PDFs that will be part of the presentation will have all of the slides. And also, past the end of this main part of the presentation, there's a bonus section which contains a number of checklists that I've used for requirements elicitation, trying to figure out what requirements should be, for requirements review and design review. And I found these checklists to be very useful in the past, and I hope that by providing them, you may find some value there too. So thank you, everyone, for coming. I'll try to answer a question or two if I see any. All right, so I have a question here from Andrew. What can you say about how an API might manage the need to deprecate certain parts? Well, certainly, the first thing that comes to mind is deprecation of API is very much language dependent. And so I can only speak with some minimal authority with C++. We do have new facilities in C++ for marking functions or member functions as being deprecated. I think the best thing is to make deprecation transparent, public, document that deprecation is coming. There are certain facilities in the standard library, auto pointer comes to mind right off the bat, which after a few years, people realize this is not a good idea, this is a bad idea, and we need to deprecate it. And so it was advertised in advance, long in advance, that this facility is going to go away. And then, you know, between C++ 03 I think it was finally fully deprecated in C++ 17, although now I'm doubting myself and have to check in C++, a CPP reference. But I guess the strongest tool for doing this is advertising. And then, of course, optimally using whatever facilities your language provides for performing that deprecation. Okay. Well, thanks for everybody. I've got to go here. Have a good conference, and we'll see you later.